when we have a supersonic airplane, the pressure on when we have a supersonic airplane and then uncambered, okay, just a flat plate, we know the pressure on the upper surface is lower and on the lower surface is higher, right? So here, I think most people answered it correctly that the pressure on the upper surface is the constant, right? Because pressure is just a function of the angle. On the lower surface is also a constant. So where is the center of lift? So at that point, I think there is a relatively small but non-significant fraction of the people say the center of lift is at the quarter chord. That's just taking the subsonic thing there for theory and applied here. Doesn't make sense, right? So if you have a pressure that's uniform, if you have suction that's uniform on the upper surface and the pressure that's uniform on the lower surface, where is the center of lift on that? At the midchord, right? So yeah. So this is I thought this is really not really aerodynamics, right? This is just simple mechanics. The center of the force is where the force is balanced on both sides, right? The total moment of all the forces around this center should be 0. And if the forces are symmetric on the airfoil on both sides, then the center has to be in the middle, right? Okay, so that's one thing. Another thing is when I said later that if the airplane has to fly subsonically, you have to put the center of gravity somewhere around the quarter chord, right? So in reality, you want to put it ahead or upstream of the combined aerodynamic center of both the wing and the horizontal tail. So putting it, the combined aerodynamic center is of course a little bit downstream of the aerodynamic center of just the main wing, right? Because you have a horizontal tail also with a non-zero area. So putting the center of the weight at the quarter chord is actually a stable configuration for subsonic flow. So the question is, at supersonic speed, how much force should the horizontal tail give you in order to achieve a balanced state? So that I think only a quite small fraction of the people got it. So again, no matter how the airplane gonna pitch, right, the center of lift on the main wing is still at the half chord, right? But the gravity operates over here. So in order for the whole thing to be balanced, should the horizontal tail be posed at a negative or positive angle of attack? Yeah, so if you have a force pulling you down here and you have a force lifting you up over here, if you don't have any force over here, which direction is the airplane going to rotate? It's going to nose down, right? Yeah, it's going to nose down. That's like what happens to a lot of the early airplanes that almost breaks the sound barrier, like the nose starts to pitch down. Okay, if you're like basically the center of lift started from here and suddenly moves downstream. That's something that could happen. Now, what force does the horizontal tail has to supply in order to prevent the nose from going down, right? It also needs to give you a force like that. And how big does the force has to be? How do you calculate how much force this has to have? Or how do you calculate the ratio of this force and this force in order for the airplane to be flying at a balanced state, not rotating? Right, I think we figured out this distance is a quarter c, right? And this distance is how many c? I think this distance, is it, I think something like this, right? I think just from the drawing, you can accumulate what's the distance from here to here all the way to here, right? Okay. So what's the ratio of this force and this force? So that the airplane can fly at balanced state, not nose down or nose up. the analysis can be done anywhere, right? But the most convenient place is to do it at just the center of weight. So if you compute all the moments of this force and this force, you have to see that this force has to be 7 times as large as this force. All right, and because the area of the horizontal tail is 4 times smaller, the lift coefficient of the horizontal tail has to be the lift coefficient of the main wing times what? Seventh? Actually 4/7, right? The area, the force has to be 1/7, but the area is 4 times smaller. Rho v square is the same, right? So the lift coefficient of this guy has to be 4/7 of the main wing. So CL of the horizontal tail has to be actually negative of 4/7 of the CL of the main wing, right? So that's the moment balance equation that we use to solve this problem. And also you also have a force balance equation, right? So the summation of the forces, the summation of this force and this force has to balance the weight. We said that we need to achieve a combined lift coefficient of 0.2. So the CL of main wing plus, because the area is 1/4, the CL of the horizontal tail has to be equal to 0.2, right? So essentially these two equations are going to combine and help you solve what is the CL of the main wing, what is the CL of the horizontal tail. Right, just two equations. One equation, force balance, another equation, moment balance. Again, this is probably something you have to work out, right, during your design, and to figure out, for example, is your horizontal tail large enough or not? Because if you ended up calculating a CL on the horizontal tail being like 10, right? That's not going to be realistic. All right. Better to have a CL less than 1, so that you have a bit of. So first of all, like the airfoil design is going to be easy, and you have some margin of safety. Okay. Any questions on that?